This is the day the Lord has made. This is the day the Lord has made. Let us rejoice and be glad. This is the day the Lord has made. Let us rejoice and be glad. There we go. All right. So happy Easter again. I know it may be like a little hard here to rejoice, especially what happened in Nova Scotia. We certainly like keep all those people who died horribly in our prayer, and especially also their families that are grieving. But the Lord has conquered death. All right. Okay. So questions.
You do 41C.
41C. All right. So 41C. Yeah, Leo? I cannot hear. I cannot hear.
Can we do
Which one? Just chat because I cannot hear. 43. All right. So 43. Let me put this here. Okay, so more people are coming late. So 43. All right. Anything else? So 41C and 43. Okay. So let me sort of share the screen. Mm-hmm. 42. Can talk, guys. All right. So you want me to do the whole thing? Okay. Why is it not like sharing? Hold on a second. So let me try this again. Come on. Share. There you go. All right. Okay, so 41C. So let me sort of look at that here. So 41C. And make sure you're here on time, guys, so that you can see here. Let me just put this here. I don't know where I can see myself. Anyway, okay, so 41C. 0.5 kilogram falls okay to the floor, then bounces a height one before you catch it. Calculate the near before it falls. Ignore frictional effect. The hemisphere as strikes the floor. How fast is the ball moving just before you catch it? Just before you catch it. All right, so here's the ball. And so you're gonna sort of catch it at a certain height of, I don't know, 1.4 meter. All right, and then you assume, of course, here that there's been like no loss here with this when it strikes. So your initial here will be at the bottom here. Fast the ball moving just before. Hold on a second. So if it falls from the shell into the floor, then bounces up to a height before you catch it. Okay, calculate before it falls. Instrument the speed of the ball as it strikes the floor, assuming it fell from rest. How fast is the ball moving? Just before you catch it. Okay, so there are a couple of assumptions here that you have to make. You have to make that there's no loss of any kinetic energy when it strikes the floor. So I don't know what was the speed with which it strikes the floor.
6.78 meters.
What's that?
6.78 meters per second.
6.87, so 6.9 meter per second.
6.78.
Yeah. So all right. So this was like the speed with which it just before it strikes. So you have to assume here that it's the same speed, right? Um, just before you catch it, just before you catch. Yeah, and then you assume, of course, that mechanical energy is conserved. So we have, um, gravitational potential energy plus kinetic energy here is equal to final gravitational potential energy plus, plus this one here. All right, and you're looking for VF. So once again, this is 0 here because HI is 0. Kinetic energy, once again, you assume it's the same as it was before. So you assume here that, VI is 6.8 meter per second. And then you just plug everything in. So if you put mvi square over 2 is equal to mghf plus mvf square over 2. You can, of course, get rid of m, and then yeah, and then you just solve for this here. So it'd be like the vi square is equal to 2ghf plus vf square. So vf will just be equal to vi squared minus 2hf, and then you just plug everything in, and you should get the right answer. Yeah, that's what I thought. Yeah. Yeah, I know. Yeah, how do you know? Like, yeah, they could have mentioned it, right?
Sir,
Otherwise,
would it
you
be
don't know. Yeah.
would it work to say I thought that when the ball rose 1.4 meters, that was the amount it rose before it lost all its energy. So the speed right before you catch it would be close to zero.
The speed, right, before you catch it. No, like what happens here? Why is it I cannot see myself here? Let me see myself. There we go. So there's the shelf here, this 1.5 meter, and this is the ground here, right? So it just fell, right? And then falls to the ground, and then of course it has a certain amount of kinetic energy. Now you have to suppose here once again that when it collides with the ground, and when it rebounds, no kinetic energy has been lost, so then it goes back up, and then just before you catch it, so what is the speed here? So that's what they're asking for.
So if you assume that some kinetic energy was lost, would
Well,
it be then fair to say that it rose 1.4 meters because the rest of the energy it lost? So therefore,
well, if you would have to know like how much energy is lost, right? So if they tell you here that you have, I don't know, 10% of energy lost, so right here, so the kinetic energy here will just be like the initial kinetic energy on its way up will just be like 0.9 times the final kinetic energy that it had just before it collided, right? So you need to know like the how much is lost. All right, okay. I don't. Oh, this is Sagan, right? Carl Sagan. Correct? Yeah, not a big fan of him. But anyway, okay. All right. So 40. So you said 40, 42. So 42. Yep. Okay. All right. So this one is a little. I mean, it's not so much like conservation of energy. Well, you can do it like using conservation of energy here, but okay. So let's have a diagram here. So you have a bullet. Whoops. So you have a bullet coming in, and the speed here is VI, what is that? The 87 meter per second. There you go. So of course inside you have friction. And then it comes out with final speed is 12 meters per second. So you're looking for the work done by friction and the average force here. And you're given here that it's 4 centimeter thick. So 4 centimeter thick. Okay. So what you can do conservation of energy here if you want. But you have friction here. So what happens here, this is equal to the work done by conservative force. Of course, the work done by conservative force is only this. You can use also work energy theorem in this case too. So what do we have here? We have the change kinetic energy plus the change in gravitational potential energy, but of course, this is 0 here because there's hardly any change in height, right? Goes so fast. So you're left with this. So Kf minus Ki is equal to work done by friction, and where S here is, of course, well, first of all, like the work. Okay. So they ask you for the work done by friction, right? So you just put everything in. So M over 2 Vf squared minus Vi squared, right? If you factor out M, and then you just plug this value here into this. Make sure that your mass is in kilogram, right? So you have to make sure that this is in kilogram, all right? You plug this in and you find what's the work done by friction. And if you want to find the average friction force, well, you just use this formula, right? So you will have had this, okay? You know what S is because S is 4 centimeter, right? So it'll be like 0.04 meter. Yeah, and then you just plug this in. Whoops, plug this in here, and then this one here, right here, and then you just isolate for the friction. Okay, are you good? Okay, 43 is it a millennium force? Okay, so millennium force. All right, so let's look at 43. All right, so you have a total coaster, there we go, is 90. All right, so initial height is 94.5 meter. What is maximum possible speed? All right, so what's maximum possible speed? And the actual speed is 41.1. Now, I don't remember who asked me like 43. Who asked me 43? Leo. Leo, are you good for the maximum possible speed? Did you get it? Leo? Leo? You got it. Okay. You can talk, guys. All right, so it's the percentage, right? It's the percentage loss due to friction. Okay, so let's look at this here. So what do they want you to find? They want you to find the percentage of mechanical energy lost to thermal energy. Okay, the change in mechanical, so the change, you remember here, so whatever, like there's any conservative force, the work done by non-conservative force is equal to change in mechanical energy. In this case here is, of course, the work done by friction, all right? So what they want to find out, they want to find out the percentage. So if they want to find out the percentage lost, it will be like how much has been lost over how much there was at the beginning, right? then times 100%. Now, this is going to give you like something negative if you don't want to, because the change in mechanical energy will be negative, because the work done by friction, of course, is negative. So you can leave it as negative if you like. All right. And what is the initial mechanical energy? Well, the initial mechanical energy is all in the form of gravitational potential energy, right? Right. It's all in the form of this. You good? All right. Now, what about this one here? So how do you find this here? Well, you have the actual speed, right? You have the actual speed. So if you go like over this here, so this minus this, so this is going to be equal to kf minus, plus this, right? Minus ki plus this, right? Now we know that at the end of the ride, there's no more gravitational potential energy, right? This is 0 here because it starts from rest, all right? And then where you're left with this. And what is kf here? Well, kf is the real one, right? So it's going to be the actual. The actual minus this, right? It's going to be the actual because it's in reality, right? If the very first question here, asks you like if there were no friction, what's the maximal speed? Maximal speed will occur when there's no friction. In other words, when the change in mechanical energy is 0. In this case, there's friction, and that's why the speed at the bottom is not as much. And then you just put this into this here, and the fact that the initial mechanical energy is equal to that. So let's do this here, right? So if I do that, so I'm gonna have this. Right, over mi, and mi is all in the form of gravitational potential energy. And then like the mass disappear here, and then you got this. There you go. So you plug all the values in. It's going to give you like something negative in this case, and that's it. Okay, so your mic is broken. Yeah, that's yeah, Madav.
Is it possible to solve this problem by setting up a ratio between the kinetic energy, the final one, with the theoretical maximum speed?
No, probably not. I'm not so sure because if you want proportionality, it has to be like directly proportional. I'm not so sure. I don't know if here, I don't think it's very directly proportional. First of all, there's a square there. Second of all, there's some subtraction. So I wouldn't do that. No. I don't know if it's going to work, but if it works, probably going to be a fluke. All right? So you do it exactly as I said. Thank you. Okay, you good? So want to have any other questions? Okay, if you did like number 44, I'm very happy with you. Okay, so I guess it involves trigonometry. Okay. All right. So I'm going to stop sharing here I'll come back. All right. So today is not going to be like terribly long. Well, I don't know. We'll find out. I may start a little bit of the topic thermal energy, right, today. And well, we'll see how it goes. Okay. So let me share this again. My computer is gonna blow up. It goes like crazy with fan. I think I should ask the board to buy me a new laptop. Okay, all right. Okay, so there'll be a title here, but I'm not gonna say it now because it gives the bunch. All right. Okay, so let's have a situation here. Let's say you throw a, don't do that, by the way. You throw a hammer towards an L. In order to drive nail into the wall. Wow. Let me sort of lift this up here. Do I have something? Fan's going crazy. Yeah, lift this a little bit. There you go. Bit of air. Okay, so once again, don't do this. It's very dangerous. All right, so here's the situation here. So you have the hammer. Yeah, not bad. And you throw it. And this is a wall right here. And then there's a nail. All right. So you made it like just a little bit in. And you want to drive this into the wall. Well, what you do, usually you just take your hammer here without throwing it, right? You swing it, right? But we'll make it, we'll just throw it here. Okay. So let's see here, like what happens here. So what you have here, you have kinetic energy. Right. So the hammer has kinetic energy by virtue of its speed. All right. It has kinetic energy. Okay, so let's see here what happens when it comes in contact with the nail. So I'm gonna make it like a little bit like bigger here. All right, so this is, right, and this is the nail. All right. So what happens here is this, is the hammer will exert a force onto the nail. Whoops. Onto the nail. All right. And the kinetic energy of the hammer of hammer goes down. As its speed decreases. All right. So kinetic energy of the hammer goes down as its speed decreases because the nail also does work on the hammer, right? In the other direction, right? Because nail does work, negative work actually, does work on a hammer. Right? There you go. Does work on the hammer. Okay, so the key point here is this here, is that the kinetic energy of hammer goes down. Okay, so let me see here. As the kinetic energy of hammer goes down, or changes, let's see here, changes. It brings about the ability to do work on another object. Do work on another object. All right, so driving the nail into the wall. All right. So as the kinetic energy here of, you remember what energy is. Energy is the ability to do work. So here what happens is that you have your nail that is at rest, and then you got a hammer hitting the nail. The hammer, of course, the kinetic energy will go down because there's work done by the nail onto the hammer. And this change in kinetic energy brings about, the ability to do work on another object, namely the nail. In the same way, the nail, let me choose a, the nail is also doing work on the hammer. All right, and by Newton's Newton's third law, these two forces are equal to each other. Okay. All right. So, so the hammer is doing work on the nail, but also now is doing work on the hammer. Okay. So as kinetic energy of hammer changes, brings the ability to do work on another object. I should also say here, increasing the speed of the nail. Okay. So the nail kinetic energy increases. So so you throw this, the nail here is at rest, it starts moving, of course, it's being driven into the wall. And what you have here is the nail like starts to pick up some kinetic energy. Of course, it's going to be, eventually it's going to come to a stop because the wall does also work on the nail, like keeping it from accelerating too much. But the key point here is this, is that as you bring those two objects, as you throw one object towards the other, there's being what we call like a transfer of kinetic energy. There's been transfer of kinetic energy from the hammer to the nail. And the hammer is doing work on the nail, but so does the nail do work on the hammer. What I want you to understand here is that the work is in the middle between those two objects. Okay. So hold on a second here. So let's go to the thing. As kinetic energy of the hammer changes, it brings the ability to do work on another object, driving the nail into the wall, increasing the speed of the nail. Nail's kinetic energy increases. But also the nail is doing work on the hammer. Okay, so decreasing the kinetic energy, hammer's kinetic energy. All right. So you remember work is the ability to do work, to do work. Now, another definition of work, I know I gave you like definition of work, like it's a scalar product between the force and the displacement of the point of application. And this is all true. But what you have to understand here also is that the work is a process by which energy can be transformed from one form to another, of one object to another object. Okay, so that's the key point here. So what we have is, right, so we have the kinetic energy of hammer, right, transform into kinetic energy of nail, right, and then through work. Okay, so through work. So a transfer of kinetic energy transfer of kinetic energy through work. So work is the intermediate. So the hammer does work on the nail does work on the hammer, and this change of energy here has been brought about by virtue of work. So now we're going to sort of write a different definition of work here. Okay, so work. Yips. So work is the process. It's a process. It's not what we call a state variable. I'm going to talk, I think I did talk about state variable before, is the process by which energy is transformed from one form to another or n transfer from one object to another object. So that's another definition here of work. Work is a process. It's a process. So kinetic energy, potential energy, we call this state variable. What does it mean, state variable of system? It means that at a given point in time, we can give a definite value. All right. So so this object here has a definite amount of gravitational potential energy. All right. So when it comes down at any point in time here, there's a definite amount of kinetic energy and definite amount also of gravitational potential energy. So this is what is called a state variable. Have you guys like learned in chemistry gas laws? Have you guys?
Yeah, we did.
You did? So gas laws here, like pressure, volume, temperature, these are all what we call state variables. It describes like the physical property of a system at a given point in time. All right. So these are called state variables. But work is a process. It's a process by which states can go from one to another, from initial state to a final state. Okay, it's a process. All right, so I thought it would be like shorter, but I guess it's not. All right, so let's do another example here. Let's say here, like John. So John pulls a block. John pulls a block across the floor. All right. So here's the situation here. So this is the block right here. And this is John right here. Okay, and he pulls this. All right. So force, pulling force. Right? So let's see here from rest. Let's put from rest here. So what has happened here is that the block was at rest. So it has no kinetic energy, and then it picks up kinetic energy. Okay, it picks up kinetic energy. So there's been a transfer here of energy. There's been work done on the box. Kinetic energy has changed. Kinetic energy has changed. It means that work has been done on it. The work is a process by which energy is transferred from one form to another, from one object to another object. So what happens here is this, is that the box is being pulled by you. So you're doing work on the box. The kinetic energy of the box changes. But something must happen. Like in order to create work, it should come as a result of a change in energy somewhere. All right. So where's this energy coming from? Well, it's coming from you. If you were to sort of pull this for 24 hours, you would get weak. Why are you getting weak? It's because you are expending what we call chemical energy. And after a while, you need to replenish your body with energy. Chemical energy is nothing else but eating. That's what eating is. When you eat an apple, you just ingest chemical energy. All right. So here, what happens here is that there is a chemical energy. So chemical energy, all right, of John, right, changes. All right, so it changes. And it brings about the ability to do work on another object, which is the kinetic energy of the box. All right. So in this case here, it decreases. And in this case, it increases. And this is done by virtue of work. So once again, the work is the process by which energy can be transformed from one form to another. In this case here, from chemical energy in U into kinetic energy of the box, or in N, transfer from one object to another object, sorry. So first of all, here you have like a change in forms, chemical energy into kinetic energy. And also it goes from one object here. It's not always true, right? But it goes from one object, which is John, to another object, which is the box. All right. Okay. So once again, work is the process by which energy can be transformed from one form to another, or transferred from one object to another object. So that's the intermediate. All right, so now what I want you to do here is I want you to find this, because I asked you to download this yesterday. So I hope you have it in your, actually it's a bit longer than I thought it would be. I don't think we'll start thermal energy. Okay, so we're gonna look at the, so here you have like a pole vaulter, and then it goes, you know, it jumps over this like super high fence or whatever it is, right? Okay, now I'm gonna ask you here, if the pole vaulter here wants to accomplish this feat, what is it that you want him to do? What did you want him like to be able to do in order to sort of make this super high jump? Anyone? Yeah, Madav.
Is it to turn the elastic energy of
No, I don't want you to talk about the energy for now. So if you want to do this, all right, so what would you want to do? Yes, Max.
Yes, to stick it into the ground.
Okay,
and then
before that, that's not enough.
he runs
Okay, tell me more. He runs
fast.
fast. That's very good. So here you want to run very, very, very fast. All right. Now he sticks the pole here into the ground. So what happens here? Try to sort of think in terms of energy transformation here. So what happens? Anyone? What happens? Yeah, Eric Hugh.
He converts his kinetic energy into potential energy.
What type of potential energy?
Elastic.
That's correct.
Energy.
It's advanced. Exactly. So what happens here is that like his goal is to run as fast as he could. He wants to gain a lot of kinetic energy. And by putting the pole into the ground, the pole does work on him, and he does work on the pole. Right? There's a transfer of energy, a transformation of energy. Now it goes from kinetic energy into elastic potential energy. Okay, now the
Can you let Jeffrey in? His computer crashed.
what's that?
Jeffrey's computer crashed. He wants you to let him into the call.
Thanks. All right, so thank you. Okay, so what does he do next? Like once the pole is bent, so what does he do next? Or she? It could be a she. Max?
He or she like propels himself upwards by jumping.
Okay, so he jumps a little bit, right? And what happens here is that the pole will regain its original form. By regaining its original form, it loses elastic potential energy. And now this elastic potential energy is converted into what? What is this elastic Rolf?
Kinetic energy?
What's that?
Kinetic?
There's a bit of but that's not the key point here, right? What do you think the key energy here? Rolf. I'll go with Rolf again. It's not so much kinetic energy here. What do you think? It's just look at the situation here. He's here and then he wants to go very, very high. Rolf?
I'm not sure.
Okay, yeah, Max?
Is it just elastic energy?
Yeah, but it's converted into what?
Oh, no, never mind. Because I thought elastic potential energy turned into elastic energy.
Elastic energy? Well, you're saying the same thing. Elastic potential energy goes into elastic energy. It's the same thing here.
No, I thought like one is like different.
No. Yes, Justin Gu. No. When we say like elastic energy, elastic energy means elastic potential energy. Electrical energy means electrical potential energy. Magnetic energy means magnetic potential energy. It's just we don't put like potential. Yes, so Justin.
Does it get turned to
I cannot hear you. And what?
Does it get turned to gravitational potential energy?
Yeah, it gains height. So all this stored elastic potential energy is getting converted into gravitational potential energy. I know there's a little bit of kinetic energy, but that's not the key point here. So let's look at this here. So let's see here. All right. So here, initially, you have kinetic. Ooh, this is big. All right, so initially you have kinetic energy, right, of running. Okay, running athlete, there we go. All right. And what happens here is, it's unfortunate they've already like bent this. I would have preferred here if it had been bent like on the ground, but anyway. Now what happens here is that this kinetic energy is transformed into elastic potential energy as the pole bends. Okay. And then finally, as it goes up, right, as athlete goes up, the stored elastic potential energy is released and converted into gravitational potential energy. All right. So these are called energy transformation. The key point here I want you to understand here is something you've learned from elementary school. What you've learned in elementary school, that energy is neither created nor destroyed. So this is called conservation of energy. And that's the title here of this whole thing here. Whoops, where is that? Oop. So the title, where was my title? Title is right here. The title, yeah, it's getting there. A little bit, there you go. So the title is Conservation of Energy. The idea that energy is neither destroyed nor conserved, just changes form from one form to another, from one object to another. So here, like in the pole vaulter, we have kinetic energy. It's been transformed into elastic potential energy, and then finally into gravitational potential energy. Plus a little bit, I know a little bit of kinetic energy. I understand that. Okay. So sometime I'm gonna sort of give you like some problems, like you're gonna have like today. There's only 2 questions, where you have to show me the energy transformation that occurs in the problem here. Okay. At some point, you have to start somewhere, right? You have to start somewhere. I mean, like, where does the kinetic energy of the athletes coming from? Well, of course, it comes from his build up chemical energy inside, right? So as he runs, he burns up this chemical energy, right, and it's get converted into kinetic energy of the individual, right? Where does this chemical energy comes from? Well, it comes from like the food that he ingested. Where is this chemical energy in the food coming from? Well, you can still keep on going back and back and back and back, right, until the Big Bang. But that's not the key point here. You have to start somewhere. Okay. So whenever I ask you like to write down like energy transformation, this is how I want you to show it to me. Little English. All right. So here you put this. So kinetic energy of athletes and now you have to, with a arrow, you show me where it gets converted into. Gets converted into elastic potential energy. Do not put only potential energy. There's so many types of potential energy: elastic, nuclear, like magnetic, electrical. So you have to mention what type. Elastic potential energy. Okay, and you put in between how is this done here. So this is as the pole bends. All right. So you tell me like how is this transformation possible? And then finally, it goes into gravitational potential energy. Well, you know what? I'm gonna put only UG. There you go. UG plus a little bit, kinetic energy. All right, but that's not the key point here. All right, kinetic energy. All right, and you tell me how. So as the pole regains its original shape. All right, so this is how I want you to show me like energy transformation. Okay, tell me what type of energy goes into what. Tell me how this is brought about, and that's it. Okay, so a little bit kinetic energy here. Little kinetic energy. Okay, but that's not a key point. All right. Okay, you good? Okay, so tomorrow, as I said, like the set up a staff meeting, virtual staff meeting at 11 o'clock. So I will not come online tomorrow. I will sort of give you like some problems that you can do on your own. You can read. I think these have already been assigned. So if they've done, that's it. It's done. If it hasn't been done, like make sure you take notes and do the problems. Okay. So you have problems for today, only 2. It's very, very easy. And then tomorrow you'll have like, you have a couple of more problems. I'll modify this. I have to sort of check, right? And I may modify some problems from for tomorrow's homework. All right. Okay, questions?
Sir.
Yeah.
So the amount of kinetic, or so the athlete like runs and then he like sticks the pole into the ground and then it gets converted into elastic potential energy. So is the elastic potential energy gained equal to the kinetic energy lost?
Well, there's always there's always a little bit of, you remember here, there's always thermal energy involved and all this. Oh, yeah. And we'll kind of talk about this in greater details, right? But the major transformation here is what? It goes from kinetic energy to elastic potential.
So it'll be like relatively like close, right?
Relatively what?
So it'll be so the values will be like kind of close to each other.
Yeah, if well, depends on the situation, but
Yeah.
here you're looking at the main, what you want, right? So of
Mhm.
course here, the kinetic energy of the athlete, when he puts it on the ground, okay, so there's elastic potential energy, but there's also like thermal energy. There's also sound energy, right? So the thermal and sound energy, this is not what you want, right? So these are called dissipative energy. It dissipates into the environment and you cannot get it back, right? Of course, you hope that you hope to minimize those two type of energies, right? Because you want really elastic potential energy. You don't want like a sound, and you don't want thermal energy. Yeah.
Mhm. All right, thank you.
Yeah, but you always put the major one, right? Yeah. All right, guys. So I guess I'll see you then on Thursday at 10:30. Okay. So I'll stay on.
Bye, sir.
Yeah, I'll stay on like for 5 minutes. Some people wants to write something, but you have to tell me, all right? And have a good day. Have a good day tomorrow too.
Bye, sir.
All right.
Bye, sir.
Bye.